Assalamu alaikum and welcome to all of you. This is a new Signal and System Foundation course with Python. This course is specially designed to help engineering students build strong concepts in signal and system, DSP, communication system, and related subjects. Based on my teaching experience, I have carefully selected the most important foundational topics that students usually find difficult. In this course, I use graph, mathematical explanation, and Python simulation to make tricky concepts easier to visualize and understand. So in this lecture, you will learn what is a signal, examples of the signals, real life examples of the signals, and with the emphasis no memorization, we build intuition visually. Let's define the signal. What is a signal? A signal is a physical quantity that carries information. It may depend on one or more independent variables such as time, frequency, space, distance, or temperature, etc. So that means the signal will vary either with time, so that signal will be called as the time domain signal. Similarly, if the signal varies with frequency, then such a signal is called the frequency domain signal, and if it changes with space, then it may be called as the space domain signals. So let's first have a look at the uh, different signals, and we'll then further discuss on this. Shown here is a temperature signal. You can see it varies with time. So it's again, this one is time domain signal that varies with time, a typical temperature signal in the summers. So you see that in the morning what it values has, and then as the day progresses, you see the temperature is increasing from say 23 up to 36. So it's a continuous time signal of the temperature. Again, it's example of the time domain signal because temperature is varying with respect to time. On x-axis we have the time, and on the y-axis we have the temperature value. The second signal shown here is also the uh, time domain signal, and this is basically EEG signal, and you'd see its variation with respect to time. Similarly, signals shown here are again time domain signals. And how do you know it's time domain? Because they are plotted versus the time. So you see on the right, on the left signal is the AC mains voltage signal, 50 hertz, and you see it fluctuates with respect to the time. So it's a time domain power or AC main voltage signal. Similarly, shown on the right is another signal, that is transient exponential decay signal. You can see mathematically it is defined as x of t equals to e power minus 2t. So that means this signal decays exponentially with respect to time. So these are few of the examples of the time domain signal graphically, and you understand what happens. On the y-axis we have the amplitude, whereas on the x-axis we have the time. So all these signals up to now we have discussed are the time domain signal. They may also be called as the continuous time domain signal because the variable on x-axis, which is time, it has continuous values. So up to now we have shown the signals visualization. That is, we have shown the signal in the graph, so you understand uh, by using graph you can tell the amplitude, and you can also say whether the signal is time domain or space domain or any other domain. And how you know that on the x-axis if it is time, then it's a time domain signal, or if on the x-axis there is some other variable such as space or frequency, so such signals will be called as the space domain signal or the frequency domain signal respectively. We can also describe signals mathematically, And if we describe them mathematically, it helps us describe them very precisely. So an equation tells us exactly how the signal changes with time. So that means we represent the signal by the equation. Examples of the signal described by mathematics are shown here. These are both of the signals which we have seen in the previous slide. That was the voltage signal and exponentially decaying signal. So using mathematics, we can write V of t, and t signifies that it is time domain signal or time dependent signal. That means it varies with respect to time. So the voltage signal we have saw on the previous slide was uh, has the equation this one 311, that is the peak value of the AC main signals. We mainly have different AC systems or the power system in different countries. In the countries like Pakistan, India, Bangladesh, Malaysia, etc., we have the 220 volt signal. So 220 is basically the root mean square value, and the peak values of this signal is 311. So that means this signal goes up to 311 in positive cycle maximum value is, and similarly minimum value is minus 311. So this signal fluctuates within this. We have seen this on the previous slide graphically, whereas here it is represented by the mathematical equation. So basically the AC main signal can be written here in the mathematical form as the peak value times the sine 2 pi f of t. So you understand, when we have 220 volt RMS value, the frequency we use is 50 hertz, whereas those countries that use 110 volt, they have the frequency of 60 hertz. So this is the frequency. Similarly, the exponential signal we have seen on the previous slide in mathematical form can be written as x of t equals to e power minus 2t. So you change different values of t and you can plot this signal as we saw on the previous slide. So in this slide we discuss about the real life examples of the signals. So signal can be speech signals such as human speech, and it is represented by varying air pressure with respect to time. So that means speed signals are also the time domain signals. Similarly, we have the electrical signals such as electrical uh, voltage or current. So electrical voltage or current variation with respect to time is used to transfer information or power in electronic systems. Similarly, other domains are the say, for example, biomedical signal. Biomedical signal can be ECG and EEG, etc. They are used in healthcare monitoring systems. Similarly, we have the communication signals. They are radio and wireless signals used in mobile communication. We also have some sensor signals. So, for example, temperature, pressure, and motion sensors outputs are the sensor signals. Or the other example can be the image signal, which is a 2D signal where intensity varies over space. Before proceeding to the end of lecture, let's have some overview of the Signal System Foundation course with Python. The course objective: based on my teaching experience, I have carefully selected the most important topics that build strong foundation for signal system, DSP, communication systems, and related engineering subjects. Learning outcome topics are graph and visualization. Then we have the mathematical explanation, and then we may have, for some of the topics, the Python demonstrations. So develop intuition for advanced engineering subjects and prepare for electrical, electronics, computer, and related engineering courses. Teaching approach is it is a carefully designed concept-based learning strategy to make tricky topics simple and easy to understand. A course outcome: after completing this foundation course, advanced topics in engineering, signal analysis, DSP, etc. will become much easier to learn. So this whole course will consist of few hours, so it's better for all of the students to have go through it. So in this lecture you have learned what is a signal, the basic concept of signals. You understand that signals carry information. We explored graphical representation, mathematical descriptions, and real-world examples of the signals. The focus is on building intuition visually rather than memorization. So in the next lecture, we'll study about the how to perform different operations such as addition, subtraction, multiplications. These are all the following lectures. So this lecture is part of Signal and Systems Foundation course with Python. So that's all from my side. See you in the next lecture.